All right, let's jump right into this explainer. Today we're going on a bit of an expedition into the absolute wild of GitHub. We're looking at a fascinating empirical study that completely bypasses the AI hype cycle and digs straight into the actual source code of thousands of repositories. We're going to find out exactly what tools and tactics engineers are literally using right now to keep giant language models running in the real world.
Because let's be real, building a massive LLM in a pristine research lab is one thing, but serving it to thousands of users simultaneously? Oh man, that is an entirely different beast. You're suddenly dealing with astronomical GPU resource demands, operational costs that can just skyrocket, and incredibly strict latency limits. If you get this wrong, your AI application isn't just going to be laggy, it's going to bankrupt you.
So, before we look at the hard data, let's quickly define what efficient serving actually means in this high-stakes environment. Basically, it means minimizing user latency, drastically lowering computational overhead, and allowing your entire system to scale without, crashing and burning. It really is the ultimate software engineering balancing act.
So here's our roadmap for this explainer. We'll hit the LLM serving bottleneck, meet the top frameworks, see how developers actually optimize these models, uncover a really cool multi-framework secret, and finally, look at real-world AI architectures. Let's get to it.
Section 1. The LLM serving bottleneck. Serving an LLM is actually a lot like running a high-end restaurant kitchen. Compute power is your kitchen staff, and memory is your pantry space. To figure out how developers are actually keeping this kitchen running, researchers bypassed all the assumptions and mined data straight from open-source GitHub repositories. By literally looking at the Python scripts and API calls, they observed the real-world survival tactics developers are hard-coding into their systems to handle massive inference demands.
And through that data, they identified the crippling survival threats developers are facing every day. You've got extreme GPU resource demands and the crazy operational costs that come with them. You've got users expecting instant responses. But the most insidious threat? That would be dynamic KV cache memory consumption. As an LLM generates words, it has to remember the context of the conversation, right? Well, this memory cache grows dynamically with every single request, acting as this massive bottleneck on how many users you can serve at once before the whole system just runs out of memory.
Section 2. Meet the top frameworks.
So the researchers filtered the noise down to 5 open-source heavyweights: vLLM, SGLang, TensorRT-LLM, LMDeploy, and FlashInfer. Now, obviously, vLLM leads in GitHub popularity with over 56,000 stars. But as we all know, GitHub stars are kind of just a vanity metric. They don't always translate to real-world adoption.
But when you look at actual repository adoption, meaning developers are actively building real things with it, vLLM is the absolute apex predator of this ecosystem. It dominates with 1,821 repositories. I mean, it leaves a staggering, massive gap between it and the rest of the pack.
But while vLLM definitely reigns supreme, it's actually pretty surprising to see TensorRT-LLM rank lowest in actual adoption here with only 15 repos. That's despite having over 13,000 GitHub stars and a ton of industry buzz. The researchers point out this is very likely due to its strict NVIDIA hardware requirements. It just makes it a lot less accessible for everyday developers compared to some of the more hardware-agnostic tools out there.
Moving on to Section 3. How developers optimize models.
This taxonomy right here breaks the developer battle plan into 2 main halves. On one side, you have algorithmic innovations, things like tweaking the model's architecture or decoding process, and on the other, you have system-level optimizations, which are all about parallel computation, memory management, and request scheduling.
And what the GitHub data revealed is honestly fascinating. Developers overwhelmingly favor the system side. Instead of attempting complex algorithmic shifts that might require retraining a model or risk degrading its output quality, engineers are heavily leaning on practical system tactics. Parallel computation lets them split massive models across multiple GPUs. Memory management directly attacks that KV cache bottleneck we talked about earlier. These are the gritty, everyday survival skills for keeping these models alive.
But how these tactics are applied really depends on the tool in hand. For instance, vLLM users generally apply a broad mix of parallel computation and memory management. But then look at FlashInfer. A whopping 88% of repositories using FlashInfer are adopting it almost exclusively for its hyper-specialized low-level kernel fusion optimizations. Users aren't looking at FlashInfer as a broad serving engine at all. They're deploying it as a highly surgical tool for intense GPU acceleration.
Section 4. The multi-framework secret. Even within a single comprehensive tool like vLLM, developers aren't just relying on one trick. They are constantly stacking methods,
heavily combining memory management with parallel computation to somehow squeeze massive models onto hardware that, mathematically speaking, just shouldn't be able to handle it.
But let's take a step back and look at combining entirely different frameworks together. Shockingly, despite its absolute market dominance, only 1.54% of vLLM repositories actually combine it with another serving framework. The vast majority of developers just treat vLLM as this all-in-one standalone engine.
But while most developers rely on a single tool, FlashInfer completely breaks the mold here. It boasts a massive 44.23% co-usage ratio. This totally proves our earlier point. FlashInfer isn't built to be the whole car, right? It's built to be a high-performance engine part that you plug into other systems to massively boost their efficiency.
Which leads us to the ultimate secret combination, deploying FlashInfer right alongside vLLM. Developers use vLLM for the high-level orchestration, handling the scheduling, the memory management, the network requests, while simultaneously injecting FlashInfer to handle the intense low-level attention mechanisms and GPU kernel optimizations. It's an incredibly powerful cross-layer optimization stack that really gives you the best of both worlds.
Section 5. Real-world AI architectures.
The research showed some really clear patterns in how these tools are actually deployed out in the wild. vLLM is basically the workhorse, used across the broadest range of model families, from tiny open-source models to those massive 70 billion parameter giants. But if you're looking to deploy a lightweight model on the edge, maybe on a mobile device or a highly constrained local server, the data points you straight to LMDeploy. Meanwhile, FlashInfer remains highly specialized, mostly used to supercharge the Llama family of models for really strict instruction-following tasks.
And what's truly exciting is seeing the actual architectures developers are building with these. These frameworks aren't just sitting around doing basic text autocomplete anymore. They're the foundational backbone for incredibly complex pipelines. We're seeing them power mathematical reasoning with reinforcement learning, highly complex RAG systems, real-time speech processing, multimodal vision understanding, and fully autonomous agent networks. It's wild stuff.
So, the absolutely crucial takeaway from this explainer is that survival out there in the wild isn't about finding one magical algorithm, it's entirely about system-level engineering. The real secret is matching the right framework, or even better, a stacked combination of frameworks to your specific hardware limits and connecting complementary capabilities across your entire serving stack.
As we wrap up this explainer, take a look at your own infrastructure. Based on the hard data we've dug into today, whether you need the all-in-one dominance of vLLM, the edge-ready capabilities of LMDeploy, or the surgical GPU acceleration of FlashInfer, you have to ask yourself, which of these frameworks is exactly what your next deployment needs to truly thrive in the wild?